To understand why classical computers face an absolute physical limit, we have to look at how they scale. As you add discrete classical bits to a system, the state space, the number of possible configurations, explodes exponentially, quickly requiring more memory than there are atoms in the observable universe to simulate complex systems. The theoretical boundary for these classical systems was established in the 1930s by Alan Turing. He proved that all digital computation can be reduced to a machine reading and writing ones and zeros on a tape. There is a persistent misconception that quantum computers break this boundary to solve mathematically uncomputable problems. They do not. A quantum computer computes the exact same functions as a Turing machine. The distinction is entirely about algorithmic efficiency, solving specific problems in vastly fewer steps. As Richard Feynman observed in the 1980s, nature itself does not operate on classical mechanics. If we want to simulate the physical world efficiently, we have to build a computer that natively operates on quantum mechanics. To understand how that hardware actually works, you have to abandon the popular analogies. Thinking of a quantum computer as simply trying every possible path at once will lead you astray. The mechanics of quantum supremacy are rooted strictly in mathematics. To see that advantage, we first have to translate familiar classical logic into pure linear algebra. In this mathematical framework, we stop thinking of classical bits as physical electrical switches. Instead, we represent them as two-dimensional column vectors. This diagram shows the standard Dirac notation for the classical zero state. Mathematically, it is a column vector with a 1 in the top indexed and a 0 in the bottom. Conversely, the 1 state is written as a column vector with a 1 in the bottom index. When a computer processes information, it runs these bits through logic gates. In linear algebra, a logic gate is simply a 2x2 transformation matrix that multiplies against our state vector. For example, the classical NOT gate, represented here by the X matrix, simply permutes the indices. When we multiply the 0 state vector by this matrix, the 1 swaps to the bottom row, cleanly flipping the state to a 1. All of classical computation reduces to this process, sequential linear transformations applied to deterministic basis vectors. Operations like the NOT gate are reversible. If you know the output, you can perfectly deduce the input. But classical computing frequently relies on non-reversible logic. Look at this equation for a constant 0 gate. Whether the input vector is a 0 or a 1, this matrix collapses both starting states into the exact same output vector. The moment this calculation occurs, the original input information is permanently erased. Because multiple inputs map to a single output, this matrix is mathematically non-invertible. This distinction sets up a famous test of computational limits known as the Deutsch oracle. Imagine a black box containing a single-bit function. We know the function is either constant, always outputting 0 or 1, or it is variable, like a NOT gate. Our goal is to determine the global nature of the function inside the box. Is it constant or is it variable? And we want to find out using the absolute minimum number of queries. In classical computing, there is a hard boundary here. You must test an input of 0, record the output, and then query the box a second time with an input of 1. Because classical matrices can erase information, evaluating the function's behavior across all inputs in a single query is mathematically impossible. To bypass that classical limit, we replace the rigid, discrete bit with a quantum bit, or qubit. Instead of occupying a single fixed point, the qubit exists within a continuous, two-dimensional complex vector space. This diagram illustrates the general state of a qubit. It is expressed as a linear combination of the 0 and 1 basis vectors, represented by the coefficients alpha and beta. Alpha and beta are not absolute physical values. They are continuous, complex probability amplitudes. These amplitudes are bound by a strict geometric rule. The sum of their squared magnitudes must always equal exactly 1. This ensures that the total probability of the system remains perfectly conserved. Because total probability must be conserved, quantum logic gates cannot be built from information-erasing matrices. Every quantum operation has to be a unitary matrix. By definition, a unitary matrix is its own inverse. Unlike the classical constant gates we saw earlier, every calculation performed in a quantum computer is perfectly reversible. The entire architecture of quantum computation relies on this reversible mathematical framework, manipulating continuous probability amplitudes rather than definite states. We visualize this continuous state space using a geometric model called the Bloch Sphere. The rigid, classical states are pinned to the absolute extremes. The 0 state sits at the North Pole, and the 1 state sits at the South Pole. To move a qubit away from these poles and into superposition, we apply the Hadamard gate. This matrix equation shows the Hadamard operator acting on a 0 basis vector. The multiplication rotates the vector precisely to the equator of the sphere. The output is a uniform superposition with equal positive amplitudes for both 0 and 1. Watch what happens when we apply that exact same Hadamard matrix to the 1 state instead. The rotation still yields a uniform superposition, but the math generates a negative relative phase in the bottom index. If you measure this qubit immediately, that negative sign is invisible. Squaring a negative amplitude still yields a positive 50% probability of observing a 1. While relative phase has no direct effect on a final, isolated measurement, it is the hidden architectural mechanism that allows quantum states to mathematically interfere with one another during calculation. We can now use this mathematical interference to solve the Deutsch oracle problem in a single query. This diagram illustrates our quantum circuit. We initialize a 2-qubit register, setting both an input line and an output line to the 0 state. First, we pre-process the qubits. We apply X gates to flip them, followed by Hadamard gates to trigger superposition. The resulting joint state is the tensor product of 2 phase-shifted vectors. Expanding this tensor product yields a 4-dimensional state vector. Notice the alternating positive and negative amplitudes. This single vector now mathematically embodies all possible input configurations simultaneously. The system is prepared as a global superposition, ready to interrogate the black box in one unified step. We pass this entire 4-dimensional vector through the oracle, represented here as a unitary matrix block. If the hidden function is constant, the matrix multiplication leaves the relative phases of our input superposition completely undisturbed. The signs in the output vector match the input exactly. If the hidden function is variable, the internal logic of the oracle reconfigures the phase relationships, shifting the negative signs within the output vector. This mathematical migration is known as phase kickback. The negative eigenvalue phase generated by the output qubit is essentially kicked backward, attaching itself to the control qubit. The nature of the function is now definitively encoded. We haven't stored it in the discrete values of the bits themselves, but strictly in the mathematical choreography of their relative phases. To extract that answer, we apply a final set of post-processing Hadamard gates to decode the phase-shifted output. If the function was constant, the undisturbed phases constructively interfere. The positive amplitudes mathematically stack, collapsing the entire vector cleanly back to the 1-1 state. But if the function was variable, the kicked-back negative phases cause destructive interference. The positive and negative amplitudes add together and cancel each other out to 0 everywhere except the 0-1 index. This destructive interference forces the system deterministically into the 0-1 state before a measurement even occurs. By reading solely the most significant bit of the final state, the function's global nature is resolved in exactly one query, demonstrating an algorithmic advantage that classical linear algebra cannot replicate. This is why the popular explanation of quantum computing is flawed. The machine does not calculate an answer by simply trying all possible paths and checking them all at once. The measurement postulate strictly prevents that. If you try to observe an expanded state space, it instantly collapses, permanently destroying the unobserved information and outputting random noise. True quantum speedup relies exclusively on the deterministic manipulation of complex amplitudes. You choreograph destructive interference so that the wrong answers mathematically erase themselves. As the physicist David Mermin summarized, shut up and calculate. Quantum supremacy emerges from the rigorous, inevitable consequence of computing natively in the complex linear algebra of nature. To understand